So now we're going to look and start exploring the beginning of calculus, really, and that is something called the derivative. So first we need to ask the question, what is calculus? Calculus is simply the study of change. Okay, so we're going to be looking at how functions change over time and how can we describe that change. Okay, so the first start for that is looking at something called the derivative. Alright, so how we're going to start this conversation. Back in Algebra 1, we learned about the first thing for rate of change, and that was looking at a linear function. We know that a linear function has the form y equals mx plus b, where the actual rate of change in this case is our value m. Okay, the rate of change of this line is looking at how quickly from point to point is the graph changing. That is our slope. Slope is a rate of change. Okay, and we find this slope m by taking 2 points on this line. So if I have a line that does something like this, I need 2 points, any 2 points, which I will call x1 and y1 for my first point, and x2, y2 for my second point. In order to find that slope, I take the difference in the y's over the distance in the x's. So basically what this says is how is the graph changing vertically compared to, as a ratio, how it's changing horizontally. We're going to keep this in mind as we go through and look at more functions that aren't necessarily linear. So what might that look like? Let's consider something like y equals x squared. Okay, simple graph that we're all familiar with, something that looks like this. Okay, so if I consider this graph, if I were to try to find the rate of change, we know that because it's not linear, at each point it is not changing at the same rate. Okay, so we don't have a uniform slope like I did for y equals mx plus b. Okay, so how could I then find the rate of change at a single point? We know that in order right now to do it, we have to have 2 points on a line. So let's picture these 2 points to start. Okay, the graph curves. So if I were to connect a line in between these two, we're going to pretend that this is straight. It doesn't touch the graph perfectly, but if I were to find the slope between these 2 points, I would get what we would call an average rate of change. Okay, it gives me on average how the graph is changing from point A to point B. But if I were to picture this second point here sliding down the curve and gradually meeting the first point, I could then, instead of having what we call a secant line where the line crosses the graph twice, it's going to slide down and eventually become a tangent line where it's touching the graph only at this point right here. If I could find the slope of that line, I would have the rate of change of the graph at that specific point. So how we can understand that is if I were to take my calculator and put in y equals x squared, and I were to click on it and zoom in on this point, and I just keep clicking and I keep zooming and I keep zooming and I keep zooming, eventually my graph in the window will look something like this. It will look linear. That's what we call local linearity. It's the same idea that if I'm zoomed all the way out, I can see the curve of the graph, but the closer and closer and closer I get to a point, the more and more the graph looks linear. The same idea would apply if I'm sitting down here on Earth in my classroom. The floor of my classroom appears flat, but if I were to fly out and sit on the moon, I can tell that in fact the ground is not flat, it is curved. Same idea. It's point of reference. The more we zoom in, the closer we get, and the more linear it appears. So if I could find the slope of the line in this window right here, it would give me an idea of how the graph is changing at the point that I would like. So how am I going to do that? Well, we need to look at this formula right here. We need to determine what is my y2 and my y1 and my x2 and my x1. So let's look at a couple of pictures just to give you an idea here. All right, this is in your notes. So I have a picture that looks like this. So let's pretend this is the y equals x squared function. If I wanted to know what the rate of change was of a graph at, say, this point right here, okay, I might pick 2 points and create a secant line. So I'm going to call this first point x1, y1, and the second point x2, y2. Now if I found the slope of that, it would give me an average rate of change, and you're going to see me write that as AROC. Well, our y values are simply the function evaluated at whatever that x is. So I could rewrite y1 as f of x1 and y2 as f of x2. Okay? So now my average rate of change becomes f of x2 minus f of x1 over x2 minus x1. Okay. All right. So we're going to continue to change the notation here as we go, but this is what we have right now for our average rate of change. Now if I picture this bottom point, if I go to the next picture down, if I picture it getting closer and closer and closer to the point that I want, it becomes a tangent line. It doesn't matter which way we go, whether we have the point curve go up or go down, doesn't matter. But eventually the points will merge. So this value down here, x2 minus x1, is going to go to 0. Well, that's simply the limits that we were doing last time, looking at this x2 minus x1 becoming 0. So, okay, now we're looking at how do I do that notation. So instead of x1 and x2, let's consider the values, and they have the notation up here in the picture. Delta x being change in x, and delta y being change in y, but we're simply going to use our f of c, f of x, doesn't matter what value. Okay, so that means my 2 points then are going to have the following labels. Okay, so I'm going to have my x value. So I have f, x, and f of x. And my second point is going to be x plus some small change. So that means my function is going to be f of x plus delta x rather than y. So now my average rate of change is going to be y2 minus y1 over x2 minus x1. So simplified, that gives me this. All this is again the equation of linear slope that you learned in Algebra 1. Okay, so this becomes my average rate of change, which is a slope. I don't want the average though. I want to picture the 2 points eventually merging onto each other. That is looking at a limit. Okay, so if we go down, then the slope then for our tangent line, which gives us an instantaneous rate of change rather than a average rate of change, is going to be looking at as the value. So right now, again, we started with this. Okay, y2 minus y1 over x2 minus x1. Remember, delta x simply represents a value. I can't plug in 2 points or just a single point to find a slope. I need 2 distinct points on a line to find the slope of it. So I want on my curve, if my goal is to find the slope at just a single point for the tangent line, I'm going to pick another point that's really, really, really close to it. And the change horizontally represents our delta x. Okay, so what I want then is this value to go to 0 because I want these 2 points to in fact be on top of each other. That is simply a limit. So if I want not an average rate of change, if I want an instantaneous rate of change, I want this bottom value here, which simplifies to simply be delta x, I want it to go to 0, which means these 2 points end up being on top of each other and become 1 point, giving us a tangent line rather than a secant line. So I then have my slope, and it becomes a limit because I want this bottom value to go to 0. Okay, I want it to become a single point. This represents our slope, and it's an instantaneous slope. Instantaneous. That would be the difference between me driving to school and saying, okay, well, I drove 30 miles in 50 minutes, and saying my average rate of change is 30 over 50 miles per minute, versus saying, how fast was I driving at minute 23 of my drive? Okay, that's kind of what we're looking at here. All right, so the definition of a derivative, it has several different notations. So let's start with all the different notations. We have, for notations, dy dx, d representing that delta, that triangle, change in. So change in y compared to change in x. You will also see it written as f prime of x. You will see it written as y prime of x. And there's some others as well, but I would say that these 3 are going to be your most common. So we're going to say the slope, they all represent slope that we learned in algebra, and that idea that we are finding the slope of a secant line and gradually making it a tangent line. So I've got the limit as delta x goes to 0 of our f of x plus delta x minus a y2 minus y1 over x2 minus x1, which simplified simply down to delta x. Now if I wanted it to be at a specific point, an x value specific, then I am going to plug in that x value once I actually do the derivative. So if I want a specific point, then f prime of c. So for instance, if I ask the question, how fast was I driving at minute 23, my c value would be 23. So I would plug that in for x. And still looking at when does delta x go to 0.